Information entropy. In information theory, the entropy, also called the Shannon entropy, of a random variable x can be viewed as the average amount of information contained within each value of x. In mathematical parlance, the average, as used here, refers to the expected value. Notation. Since the letter E was already in use to represent the expected value of a random variable, the uppercase variant of the Greek letter eta, which is H, was chosen to represent entropy. Given a discrete random variable x with n possible values, x1, x2, up to xn, and associated probabilities p1, p2, up to pn, the entropy h of the random variable x is defined as h of x is equal to the expected value of I of x, which is equal to the following finite sum, where I of x sub I, which is equal to log base 2 of 1 over p sub I, is classically interpreted as the amount of information received when learning that x has taken on the value x sub I. In other words, the entropy of a random variable is simply a weighted sum, where the amount of information received for each value of x is weighted by the probability that x takes on that value. Example 1, coin toss. Let x be a random variable that takes on value x sub I with probability p sub I. We see that the information content of knowing that the outcome is heads is equal to log base 2 of 1 divided by 0.5, which is equal to 1. The same holds true for the information content in knowing that the outcome is tails. Constructing our finite sum, we obtain the entropy of the random variable x and find it to be 0.5 plus 0.5, which is equal to 1 bit. The above calculations reveal a general property of the expected value function e. The expected value of equally likely outcomes is equal to the arithmetic average of the outcomes. Consequently, we should not be surprised that the entropy of x, in this case, is equal to the information content of any one of the outcomes, i.e. values, of x. For future use, we generalize and document the above results. Equally likely outcomes. Let x be a random variable consisting of equally likely outcomes, each having probability p. The entropy of x can be calculated as follows: log base 2 of 1 divided by p. Example 2. Weighted coin toss. Let y be a random variable for the outcomes of a weighted coin toss, where the probability of heads is 0.75 and the probability of tails is 0.25 for each toss. The information content for each of these two possible outcomes will be 0.415 for heads and 2 for tails. Consequently, our weighted average leads to an entropy calculation of the following: 0.31 plus 0.5, which is equal to 0.81 bits. Example 3, card selection. Given a deck of 52 cards, let x be a random variable that takes on values x sub I with probability p sub I, as listed below. The entropy of the random variable x is therefore 0.5 plus 0.5 plus 0.5, which yields 1.5 bits. This means that the average amount of information received when learning the value of x is 1.5 bits. In the next 3 sections, we drill down to what information entropy is actually telling us. We will consider 3 interpretations of entropy and then specify which meaning of entropy will be of most value to us. I should emphasize, however, that each of the interpretations we will consider will broaden and deepen our understanding of information entropy of a random variable, enabling us to more effectively apply this powerful concept. Entropy, a measure of the efficiency of an encoding. Recall that Claude Shannon's definition of information entropy resulted from his desire to find a way to efficiently send messages without losing any information. Although we will not need to encode and transmit messages electronically, a little understanding of encoding fundamentals will go a long way. For example 3 in the previous section, we calculated the entropy of the random variable x to be 1.5 bits. Having explored the idea of a non-whole number of bits before, we conclude that 1 bit is insufficient to uniquely encode the values of x, while 2 bits, in some sense, are more than what is actually needed, leading to wasted resources. Informally speaking, a good strategy for efficiently encoding the outcomes of a random variable consists of the following steps. Determine, if you can, the shortest bit strings needed to uniquely represent all of the outcomes of your random variable. 2. Inversely pair bit strings with outcomes. That is, assign the longest bit strings to the least probable outcomes, and the shortest bit strings to the most probable outcomes. Let's apply this strategy to the random variable x in example 3. 1. Any 3 of the 4 2-bit strings 00, 01, 10, and 11 could be used to uniquely represent the 3 outcomes red, clubs, and spades. But can we judiciously choose just 2 of them together with a single digit? Yes. Consider the 2-bit strings 10 and 11 along with the individual digit 0. These can be used to uniquely represent 3 distinct outcomes without leading to ambiguity when these strings are concatenated in various combinations, which would represent a sequence of successive card selections. Whereas 10 and 11 together with the single digit 1 would not work, since these assignments lead to ambiguous sequences of zeros and ones, such as 1110, which could be interpreted as either 1, 11, 10, or 11, 1, 10. Can you find another trio that would work as well as 10, 11, and 0? 2. We pair the shortest bit string 0 with the most probable outcome, namely red. Each bit string 10 and 11 can be paired with either clubs or spades, since these bit strings have the same length and the outcomes clubs and spades are equally probable. Because these last 2 assignments are arbitrary, we will pair 10 with clubs and 11 with spades. Therefore, the average number of bits per value of x for the above encoding is 1 bit times 0.5 plus 2 bits times 0.25 plus 2 bits times 0.25, which is equal to 1.5 bits. Observe that we were able to achieve the minimum number of bits set by the entropy of the value of x, which is 1.5 bits. But if we had been careless in our encoding, this might not have been the case. For instance, if we had assigned the bit string 0 to clubs and the bit string 10 to red, then the average number of bits per value of x would have been 1 bit times 0.25 plus 2 bits times 0.5 plus 2 bits times 0.25, which gives 1.75 bits. If we had to transmit on average more than 1.5 bits per value of x because of a poorly designed encoding, then we would not be making the most efficient use of our resources. On the other hand, an inadequate encoding that results in transmitting, on average, fewer than 1.5 bits, then we would not be sending enough information to resolve the uncertainty about the specific values of x that we want to convey. In other words, the entropy of the random variable x is a lower bound on the average number of bits per value of x we need to transmit. Using less than this number would not be good if the goal is to unambiguously describe the sequence of values of x we want to transmit. In other words, our encoding scheme would have fallen short of accomplishing what we set out to do. The following diagram summarizes the three situations. Technical note: although it may not be possible to encode a random variable x in a way that immediately achieves the lower bound set by its entropy, it has been proven that there will always be an encoding, such as a Huffman encoding, whose average length approaches h of x as the average block size goes to infinity. Entropy as a measure of the efficiency of a binary inquiry. The entropy of a random variable x can be interpreted as the minimum number of binary questions, on average, that need to be asked to determine the identity of a random value of x. Example 1. Let x be the random variable for a fair coin toss. In the last section, we calculated the entropy to be 1 bit. This means we should be able to ask just one binary question per coin toss in order to determine the outcome of a random toss. This is clearly the case since either of the questions, is the outcome heads or is the outcome tails, is sufficient to identify the specific outcome with certainty. Example 2. Let x be the random variable of a die roll for a 6-sided fair die. Since the outcomes are equally likely, we can use equation 5 to obtain an entropy value of 2.585 bits. This means that on average, we should be able to ask approximately 2.6 binary questions per die roll in order to determine the exact values of the die in a sequence of random rolls. Since we cannot ask 2.6 bits regarding the outcome of a single roll of the die, we would need to ask at least 3 binary questions in order to guarantee that we can determine the outcome with certainty. A binary decision tree can be used to model the various paths we might take as we ask our questions. The goal is to ask the most informative questions, ones that resolve the most uncertainty regarding the identity of the specific outcome of the random variable. Decision tree, a flowchart-like structure in which each internal node represents a test on an attribute, for example, whether a coin toss comes up heads or tails. Each branch represents the outcome of the test, and each leaf node represents a class label. The paths from root to leaf represent classification rules. In general, a good strategy is to divide the data in half, or as nearly as possible, and then to ask the following yes-no questions. Is the value of the randomly rolled die among the numbers 1, 2, or 3? Or is the value of the randomly rolled die among the numbers 4, 5, and 6? The answer to either question will narrow the possibilities down to 3 distinct values. Once these three values are identified, we divide the pertinent set into a singleton and a doublet, such as the set consisting of 4 and the set consisting of 5 and 6. From here, there are two possibilities. 1, we have found the exact outcome of the die roll, or 2, we divide the doublet into two singletons, such as 5 and 6 becoming the singleton set 5 and the singleton set 6. Below is an example of a binary decision tree in which we identify the outcome of the roll to be 5. So if we use a binary decision tree as depicted above, what is the average number of questions per die roll that would need to be asked in order to identify the specific value of a random die roll? To answer this, we first need to determine the lengths of paths, branches, and then the number of paths of each length that end at a singleton. The 2 question branches are paths of length 2. The 3 question branches are paths of length 3. The corresponding number of each type are listed below. Hence, the average number of questions per die roll that were asked is 2 times 2 plus 4 times 3 divided by 6, which comes out to be approximately 2.667. We compare this answer to the entropy of x, which is log base 2 of 6, which is equal to 2.585 bits. Observe that the entropy calculation of 2.585 bits is smaller than the 2.667 number of binary questions. Recall that the entropy of a random variable x can be interpreted as the minimum number of binary questions, on average, that need to be asked to determine the identity of a random value of x. Therefore, the entropy for a fair die roll is a lower bound for the average number of binary questions that you would have to ask in order to determine the value of a particular roll of the die. In general, you may not be able to attain the lower bound using a binary inquiry scheme. But an economy of scale kicks in when you consider sequences of random variables of x and are judicious in designing your binary inquiry, as the next example demonstrates. Example 3. If you consider tossing a fair die twice, you can reduce the average number of binary questions per die roll from 2.667, as before, to 2.611. But how? By formulating questions that involve more than the outcomes of a single die roll, you can tease out more information per question. I illustrate this idea on the next page, where I reduce the average number of binary questions per die roll from 2.667 to 2.611, which is only 1 percentage point away from the lower bound set by the entropy of x. To mitigate tedium, I will complete the binary decision tree for 1/4 of the data. Then, by symmetry, the average number of questions per die roll for this fourth of the data will also be the average for the entire binary decision tree. The full set of possible outcomes for a double die roll is as follows. For the first digit in each double-digit number is the value of the outcome of the first die roll, and the second digit is the value of the outcome of the second die roll. Here is our partial binary decision tree of a double die roll. Observe that for the binary decision tree above, we have the following. The number of 3 question branches is 7. The number of 4 question branches is 2. But to arrive at the starting set 11, 12, 13, 14, 15, 16, 21, 22, 23, 2 binary questions would need to be asked. Thus, the true lengths of the question branches are: the number of 5 question branches is 7, the number of 6 question branches is 2, Hence, the average number of binary questions per die roll is 1/2 times the quantity, 7 times 5 plus 2 times 6, that sum divided by 9, which comes out to be approximately 2.611. If we use the same system of binary questions for the other 3/4 of the full decision tree, we will find that the average number of binary questions per die roll needed to be asked to arrive at each of the 36 outcomes of a double die roll is the same as the above. In summary, we reduced our initial estimate of 2.677 binary questions on average per die roll to about 2.611 questions. This brings us considerably closer to the minimum value set by Entropy, which is 2.585. Interpretation of decimal answers. We can interpret our answer of 2.611 binary questions per die roll as telling us that if we were to roll a fair die, say 10 times, we would expect about 26 binary questions to be enough to determine the actual outcomes of all 10 rolls. In the next section, we give a final interpretation of the entropy of a random variable as a measure of surprise. In information theory, it is formally called surprisal. Roughly speaking, the more surprise we experience upon observing a particular outcome, the more information that outcome provides. Said differently, when an unlikely outcome occurs, it is not only surprising, but it also provides us with more information than a likely outcome. In the next part of this series, you will look at entropy as a measure of surprise.